formulation or short notation of galvanic cells. Now look here how you write this galvanic cell short notation. Now this is suppose that the two cells and there are two electrodes which is dipped in their of its own ion solution. So how do you represent these cells? Now this is short bridge. Okay. Now always you have to write in this way of that format, like right side always cathode, left hand side always that anode. Cathode is denoted positive, anode is denoted by negative. Now in between this is short bridge. Now just pick up this example. For example, this is the way of that. Magnesium electrode is in contact with that in G2 plus 1 molar. So electrode is represented by single vertical lines, and that the in between these two double vertical lines is nothing but what? Short bridge. Okay. So magnesium electrode is in direct contact with of its own solution, magnesium sulfate suppose, and Ag plus, this is Ag solid, this is electrode is in direct contact with that Ag plus, that is 1 molar solution. So the way of that. So generally again that 1 molar solution, aqueous solution should be in the middle part of this in notation or that formulation of that in galvanic cell. This is generally formulation of that the galvanic cells. Now double vertical lines indication will show that the short bridge is present, or the connection of these two solutions, this look here, short bridge is present. Outflow of electrons is generally here. In the notation, formulation that electron just flow, that is anode to cathode. Let us see writing of that cell reaction. Now we will study how this the cell reactions from the right. Okay, this is suppose just example. Nickel formula is in contact with that Ni2 plus 1 molar and double vertical line, that is the short bridge here 3 plus 1 molar, and then is in contact. This is that aluminum solid. Okay. Now here this is cathode side and this is that the particular the anode sides. We know that at anode always oxidation and cathode always that reduction, gain of electron, loss of electron. So first reaction what will be here? Nickel solid is here. Nickel is converted to Ni2 plus. What is mean of this? This is just this is 1 molar. So losing of these 2 electrons, loss of electron. This is here reduction. So oxidation, loss of electron. Now second one is what? Al3 plus converted to Al solid. Means what? This is that the gain electron. 3 electron is gain. Aluminum solid. So Al3 plus 1 molar plus 3 electron gain is here, and aluminum solid is formed. Now you have to balance the electrons. So what you have to do is multiply this equation, that is 3, and this is that second equation by 2. So multiplying, that is here suppose that the 3 and here that is 2. So what will be happening if you multiply here? So there will be the changes. Now such changes is taking place. If you multiply here 3 nickel, here this again 3 and 3 into 2 6. Now if you multiply here 2, that is 2Al3, 2 into 3 6, and this is 2 here. So what happened here? So therefore 6 electron get cancelled. 3 nickel solid plus twice Al3 plus 1 molar gives here 3 nickel 2 plus and twice aluminum, that is solid, and this is 1 molar. This is going to study electrode potential and cell potential. Now these two are related to each other. How this is that? One single electrode potential is developed one electrode, and another single electrode potential is developed other electrode. If you join these two, if you do algebraic sum of these two electrode potential, then you have the cell potential. Now what is electrode potential? Electrode potential is the potential difference established or obtained due to the half cell reaction. Okay, due to the half cell reaction at the electrode surface, that is called as electrode potential. For example, zinc rod or zinc metallic plate dips of its own ion solution. For example, zinc electrode dip ZnSO4 solution, zinc sulfate. That time the electrode potential is developed on that zinc electrode. Now what is cell potential? Now cell potential, look here. Cell potential is the algebraic sum of these two electrode potential. So therefore we can write like this: E cell is equal to E oxidation plus E reduction. Now cell potential, how do you define that? It is the potential difference between the electrodes corresponding to the external crop electrons from anode to cathode, or the same potential is also called as EMF. So electromotive force or cell potential is also defined as it is the potential difference which is responsible for flow of current from higher potential electrode to the lower potential electrode, or potential difference which is responsible for flow of electrons from anode to the particular cathode, because the flow of electrons is opposite to the current direction. The next point is that standard potential. Now standard potential means what here? The potential measured under standard conditions. The voltage is measured under standard conditions. Standard condition, chosen the standard condition is that particular the concentration of solution should be 1 molar. Then the pressure for that the solutions or that the gases, liquid, solids 1 atmospheric pressure and at 25 degrees Celsius. Under these conditions, you measure voltage at that time called as that standard potential. Now we know that standard potential is denoted by E naught cell. Okay. Therefore, E naught cell is equal to, how do you write? E oxidation at anode plus E reduction at cathode. Therefore, one point is here to note down. Standard reduction potential and standard oxidation potential of any electrode is always equal, but just sign is reverse. Their sign is only opposite. Another, they have given according to the IUPAC convention, any potential of electrode so is mentioned, recorded as, that is the here standard reduction potential. Okay. So according to IUPAC convention, standard potential of an electrode is taken as the standard reduction potential. Okay. So here E oxidation. Now E oxidation and not replaced by E reduction, because this is the term just equal to each other. Now if you replace by this sign, by this term, so therefore above equation becomes like this. Now put down this term is here E reduction anode plus this. Therefore you are getting this second step, and finally standard electrode potential, standard cell potential is equal to that. This is that just electrode potential, standard electrode potential at cathode minus standard electrode potential at anode. Now we are going to study dependence of cell potential on concentration, which is given by Nernst equation. Now Nernst equation is how here applicable. Now to decide or to predict the spontaneity of reaction for anything other than standard concentration condition, we should know for that purpose how the voltage of galvanic cell is varied with concentration. For that purpose, this point. Therefore, dependence of cell voltage on concentration is given by Nernst equation. So the Nernst equation, how this is they have given. Just consider first, let us consider general reaction like this: A plus B gives C plus D. Now this is stoichiometric coefficient small a, b, c, d. Now therefore the cell potential is given by is equal to standard cell potential minus RTNF log to the base E concentration of C, D concentration of A and B, raised to power that small letters. Okay. Now therefore log to the base E convert log to the base T. So that time 2.303. So therefore this step is converted into this minus 2.303 RT NF log to the base T, and that is the way out. Where N is the number of moles of electrons used in reaction, F is the Faraday 96,500 coulomb, T is temperature in Kelvin, and where R is the gas constant, which is having the value 8.314 joule per Kelvin per mole. Okay. Now at 25 degrees Celsius, if you put down in this case, in this term value RT, that is gas constant, temperature, and this gap, that is 96,500, then you are getting this value 0.0592 volt. This value. Now this term value, see here this equation number 1. Here in that is equation number. Now if you put down here this value, so you are getting this equation. This equation converts into this. E naught cell minus 0.0592 volt, then log to the base 10 concentration of C divided by concentration of that, the A into B. So concentration of products divided by concentration of reactants. Now if you consider concentration of that reactants and products is in unit 1 molar, that is concentration of A is equal to B equal to C is equal to that D. Okay, so that 1 molar. Therefore, you are getting E cell is equal to E naught cell. So this is fine. Now the Nernst equation is useful for that to calculate. You can calculate cell potential of any galvanic cell. Then you can calculate electrode potential also. This is the application of this equation. We are going to study a particular problem. Read this problem first of all. Calculate the voltage of the cell. The given cell is this. Okay. This is the way of that. Given cell is like this galvanic cells. 10 is in contact with the SN2 plus, double vertical in the vertical line indicates solid bridge. This Ag plus is in contact with these solids. They have given this standard reduction potentials of that T and Ag. Now calculate voltage of the cell means you have to calculate cell potential, and therefore cell potential formula for the Nernst equation you have to apply. So this is that particular formula. First of all, we have to calculate that the value of that this E naught cell by using these two values. Then also what we have to do also, write the cell reaction from this galvanic cell given this cell, and then from this cell reaction we can obtain that particular the net cell reaction. Okay. Now this is the first one, oxidation half reaction. Second one is the reduction half reaction. T is converted into T2 plus, Ag plus, gain 1 electron convert to Ag solid. So multiplying by these two here, because these two electron get cancelled. Finally you are getting this particular equation. Now the second one is that E naught cell is calculated by using these two values. Okay, so minus is plus here, therefore you are getting 0.936 volt. Now the next step is this, using this particular formula. Now read this, that E cell is equal to E naught cell minus 0.0592 volt upon the log to the base 10 concentration of that SN2 plus, that is T2 plus and Ag plus. So raised to power 2. Why? Because in this chemical equation you have to multiply this 2, because this reduction half reaction, this is 2 is here multiplied. That's why the way of that. Then put down this value, then you are getting this particular equation. Then next step is what? So the getting this log up to the base 10, that is 200. So for characteristic that 2 and log of 20, that is you can see that 0.3010. So putting down this value, you are getting last this value, that is cell potential 0.8679 volt.